In this video, we're going to do some guided exam question practice on the 2019 Junior Cert Science question 15. It was a mixture of different chemistry topics, so you couldn't really pin it down to one area. This is the first time that we're seeing one of the last two questions. So on the exam paper, like I went through before, there are 16 questions, but the last two, number 15 and number 16, are worth 45 marks each. And that actually means that this question here is worth 12.5% of the exam, so quite a big chunk. So together, question 15 and 16 make up a quarter of the paper, even though it's only two questions. So these are the longest questions, and it works out that you've got about 15 minutes to do these questions on a paper, at least 15. I would focus heavily on these two questions. So what I want to do is get your timer and we'll get stuck into it. Timer for 15 minutes and we'll get cracking. All right, so first of all, let's read the blurb. There's a bit of a text here. There's a bit of a blurb. It says, the periodic table was developed by Dmitry Mendeleev. So he was a Russian chemist. Won't really worry too much about him. It says here it was published 150 years ago in 1869. To celebrate the International Year of the Periodic Table, the European Chemical Society has designed a new kind of periodic table called the 90 elements that make up everything. So if you can see this picture and it looks all funny, it's supposed to look like that. That's the first thing. It's where they've designed the periodic table in a different way to kind of show the relative amounts of each of the elements that make up the different substances on Earth. So it's kind of showing how much of each one there is around, and the different colors show where they're used or how endangered they are, if you like. How close are we to running out of these elements? So that's what this periodic is. Probably not like any periodic table you've ever seen before, as it's important to remember it's supposed to look like this. It's got a few different functions here, this table. All right, so let's read the color key here down below. So again, I'm going to get you to pause the video now and read what each of the colors means. All right, so you see anything in that's got the little white phone, if it's got this symbol here in them, for example, hydrogen is here, that means it's used in smartphones, to make smartphones. Green means we're not in any danger of running out. There's loads of it in the world. Yellow means it's got limited availability. So we're starting to get a little bit short on this. We've got a risk to their supply. We may run out of this if we keep using them irresponsibly or unsustainably. Orange means it's the threat to them running out is getting bigger. So we're getting closer to being completely out of this substance. And here in red, the availability of these elements are completely threatened. So within the next 100 years, we may actually run out of this stuff. There may be none of that element left. Crazy idea to think of that, but this is what happens if we keep using this stuff and then throw in the products that we're producing using these chemicals, we throw them away. Now, there's a lot of unnecessary crap in there. You'll see when we get down to the questions what it's actually asking us to do. Okay, so it says that the table has been drawn so that the area occupied by each element indicates how much of that element is in Earth's crust and the atmosphere. So these two areas on the surface of Earth and in the atmosphere, the size of the box. So for example, oxygen here is quite a big box, and that's because between all the stuff, the compounds in Earth's crust and the oxygen in Earth's atmosphere and all the gases that contain oxygen, it's a very plentiful, there's loads of it. All right, let's just crack on with the questions now. We'll get stuck into them. So here, let's get into part A. So it says from the table, identify a gas which is a component of Earth's atmosphere and which is in plentiful supply. So a couple of things here. We need something that's in plentiful supply. It's in Earth's atmosphere, and it has to be a gas. Okay. Now, there's nothing up here to tell us whether stuff is a gas or not. So you need to know which ones are gas, and you need to know which ones are plentiful and which ones make up Earth's atmosphere. So pausing the video and writing down a gas that meets all of them criteria. Plentiful supply, it's in Earth's atmosphere, and it's a gas. So I'm going to show you the table, and I'm going to pause the video and write down the answer. Okay, so the first thing I would say here is it has to be an element. So something like carbon dioxide is not really relevant here because it's not an element. So we need an element that's in the atmosphere. The two big examples I would pick here are nitrogen and oxygen. Both of them gases are in the atmosphere. Probably oxygen is probably the one that's the most obvious. So why does this fit our criteria? It's a gas, good. It's in Earth's atmosphere, good. And it's in plentiful supply because it's green on the table. Nitrogen, for the same reasons, would work as well. Okay, all right. So that there would be oxygen. Let's jump to the next question. Why should the use of the gas helium in birthday balloons be avoided? So most of us have seen the idea of the helium balloons. They're the ones that keep rising up. If you let them go off the string, they go into the air and they're gone. So it's saying, why should the use of helium be avoided? So why should we stop using helium balloons? All right, so I'm going to go show you the table again. All right, now if you don't know where helium is, you kind of need to know what the symbol for helium is. All right, so I'm gonna, if you're not sure that, you can go ahead and grab your periodic table and find out what the symbol for helium is. Do that now. All right, you'll have seen that helium's symbol is here. It's He. Now, red means that it's seriously threatened. Its availability is seriously threatened in the next 100 years. So if you didn't know that, now put together an answer why we should avoid using them in balloons. Okay, so you should only be writing if you've written an answer for this now. So why should we avoid using helium? Helium is, and let's use the word it says here, it's seriously threatened. Its availability is seriously threatened. So availability is seriously threatened. You can fit it in, well, you could have said something like this, it could run out, or it will run out if we keep using it irresponsibly. No, I'm not going to write that. Its availability is seriously threatened. That's what it told us, so that's what we should write. The next one, it says the element indium, and here it gives you the symbol In, indium, is used in smartphones. At current usage rates, indium will be used up in the next 50 years. Suggest one way in which humans could contribute to sustaining levels of this element for future generations. So we want to sustain it. So do some kind of practice where we are making it so we will not run out of this element, indium. Let's just go to indium on the table up here. Let's find it. Where is In? Here it is, look. And we see that it's red. So it's threatened in the next 100 years. And in the question, it actually says it's going to run out in 50 years. So how can we be more sustainable with indium? Sustainable indium. All right, pause the video, write down an answer. All right, so sustainability, you guys all know sustainability, one of the cornerstones of that is reduce, reuse, recycle. That's a pretty good motto for sustainability, reduce, reuse, recycle. So now that I've given you that, if you didn't already know or write an answer for this, you should be able to write an answer to this now. And make sure we're referring to the problem in the question. Pause the video, do that now. All right, so it says that the big thing about indium is that it's in smartphones. It's used in smartphones. So what could we do in terms of this here that would help make it more sustainable? Okay, so what we could do is we could make choices like buying more second-hand phones, buying more recycled phones, buying more recycled mobile phones. Instead of always buying new ones, try and recycle the old ones, or even not necessarily buy secondhand ones, but can the companies who make the phones reuse the parts again that have indium? Instead of dumping them in the ground and using more brand new indium to make a new one, can we instead use the old parts to make a new phone? So buying more recycled mobile phones, reusing the parts of old mobile phones, parts of old phones to make new ones. So anything like that, that would make this more sustainable and stop us throwing out old stuff and just using brand new stuff to make new phones. So some kind of answer like that. Now let's jump to the next bit. It says here, the diagrams on the right show the arrangement of particles in the elements aluminium and chlorine at room temperature. So here's aluminium and here's chlorine. This is at room temperature, so around 20 degrees Celsius. What evidence is there in the diagrams? So we've got to use evidence from the diagrams to support the classification of these substances as elements. Evidence. So what about the diagram tells us that these are elements rather than compounds or mixtures? So pause the video and talk about what evidence in the diagram tells us this. Okay, so you should only be listening if you've written an answer here. So remember, keep it labeled D, and we're in the box here. And it says, well, the evidence here is that aluminium has all this one type of atom. They're all blue atoms. There's no other type of atom there. That's what elements are. Elements are substances made of only one type of atom. Chlorine as well. Yes, the atoms are in groups of 2, but you'll notice that they're all green. They're all the same types of atoms. So that there is the evidence. So what evidence is there? Chlorine and aluminium are each made of only one type of atom, one type of atom or particle. So there's only blue ones, there's only green ones. Okay, that's your evidence. If there was, say, for example, a red one attached to a black one, like that, well, that would tell me that this is not an element, because this is 2 different types of atoms. So this here is not an element. There's different kinds of atoms there. It has to be something else. In the next question, which of these elements is a solid at room temperature? Justify your answer. So again, solid. Looking at the diagram, what tells you which one is a solid? Pause the video. Okay, so choose which one is an element. Which one? You should have chosen aluminium. Don't forget the second part of the question. Justify your answer. So I always say it's a good idea to label what you're doing so that you can't miss. Which one's a solid? Aluminium. Justify it. Why? So if you haven't justified, pick some evidence from the diagrams that tells us that aluminium is a solid. Pause the video, do that now. The evidence that I'm looking for here is that the particles are all touching. They are regularly arranged. So they're in a nice repeatable pattern, regular arrangement. That's what solids are like. Next bit, it says aluminium reacts with chlorine to form a compound called aluminium chloride. Use the periodic table on page 79 of your formula tables booklet to predict the ratio of aluminium to chlorine in this compound. So predict the ratio, how many aluminium atoms for how many chlorine atoms, and therefore write the formula of aluminium to chloride. So the ratio we're looking for is how many aluminiums for how many chlorines. Okay, so in what way will they combine? So here is your periodic table that they're talking about here. All right. So what I'm going to do is I'm going to stop and I'm going to give you a chance to try to do this by yourself. I have showed you how to do this before. If you're in my class, if you're not in my class and you're watching this, maybe you have been shown a way to do this. I want to give you the chance to do it by yourself. What's the ratio of aluminium to chloride when they combine? Pause the video and do that now. All right, so a reminder of how we do this then is, well, on a periodic table, we know that each of these things here is a group. Okay, so each of these vertical columns is a group, and the groups have numbers. But they also have this thing called a valency, okay? And this refers to how many bonds the elements form when they join together. So when they join with other elements, they want to form a certain amount of bonds. The valency of group 1 is 1. The great valency of group 2 is 2, so that's easy. So the valency of these first few is the same as their group number. This here is group 3, and the valency is 3. This is group 4, and its valency is 4. Now, when we get to group 5, it starts to reduce again. It goes 3, 2, 1, and 0. So this refers to the number of bonds that they'll form. And sometimes you'll see it written like this, where this here is +1, this here is +2, this here is +3. This here can be plus or minus 4, it doesn't really matter. This one is -3, -2, -1. And what we've got to do is when we're combining them, we've got to make sure that the valencies balance, okay? So in this case, let's find aluminium and chlorine. Let's find aluminium and chlorine. Now, aluminium is in group 3. Look at it here. This is aluminium, which means it's got a valency of 3. It wants to form 3 bonds, or it's got a +3 charge if it forms an ion. Some of you will know what that means if you're in my class. And then chlorine is over here, and it's got a valency of -1. And we need those valencies to balance out. So what do I mean by that? Well, if we've got an Al and it's got a valency of 3 or +3, Think about Al plus 3. How many chlorines do we need to add to it if they have a valency of 1 or -1? They need to be balanced at the end. So pause the video and write down how many chlorines for how many aluminiums. Okay, so hopefully you figured out that 1 aluminium will combine with 3 chlorines. If you did this by yourself, well done. If you did it with a bit of help, still well done. Okay, so Al with a valency of 3 will join with chlorine with a valence, 3 chlorines with a valency of 1. This gives us the final formula, so don't forget what it says here, hence write the chemical formula for aluminium chloride. So chemical formulas we write like this. There's 1 Al, so we just write Al, and then it's combined with Cl, and there's 3 of them. So we use this little subscript to show that there are 3 aluminiums. And this here is the final answer for the chemical formula for aluminium chloride. If that doesn't make any sense to you, I advise you to go back and watch the video where we did how to predict the formulas of compounds when they join together. All right, let's go to the next bit. It says here, elements can be classified as metals and non-metals. So unrelated to the exam paper here, I want you to think about this, this periodic table here and predict where the metals are on the table. Again, if you're in my class, we've done this, I've shown you where they are. Where are they on the periodic table? Okay, I'm going to remind you, if you're struggling here, I'm going to show you there's a division using this stepped line that shows where the metals and the non-metals are. It's a stepped line like that begins under boron. Look, so here is boron. It begins under boron and it goes down in a step like this. So the question I'm asking you, and it's a quick bit of revision, are where are the metals? Are they on the left or are they on the right? So if you're not sure, look at some of the names or look at some of the symbols and see which ones are metals. Okay, so for example, oxygen, we know that's definitely not a metal. Most of you guys know that oxygen is a gas, definitely not a metal. Chlorine, definitely not a metal. Fluorine, definitely not a metal. So all these on the right, these must be non-metals. Non-metals. And that means that everything over here, these are the metals. So that was a quick bit of revision. Where are the metals and the non-metals? All right, over here, it says elements can be classified as metals or non-metals. The table shows some properties of the 3 elements from the periodic table. So we've got no name, element 1, element 2, element 3, and here are some properties: melting point, boiling point, and whether they conduct electricity or not. Right. So applying a little bit of theory now, which element, 1, 2, or 3, is most likely to be a metal? So elements, which element is what you were asked. So pause the video, write down which element is likely to be a metal. All right, you should have written element number 1. So element 1 is likely to be a metal. 1 is a metal. Now, don't forget, there's another bit to this question. That's why I split it up for you. Justify. Justify means give a reason. What's the reason why 1 is a metal? So if you said 1, well done. If you didn't, then change it to 1. Why is 1 a metal? How do we know this? Pause the video, write down your answer. Right, so there's a couple of reasons. So the first thing is that we know metals are good conductors of electricity. So yes, it's the only one that conducts electricity is element 1. Also, if you look at the melting and boiling points, they seem to have a very high melting and boiling point compared to the others. And metals are all solids at room temperature. You've got to heat them up generally to get them to conduct. So it's a good conductor. Is one reason. With a high melting point, NP, and boiling point, BP. Now, you don't need all of that. Probably if you just said it's a good conductor, that would give you it. And if you said it has a high melting point and a high boiling point, that would give you a justification. You don't need both, but again, why not show off if you know this? Next one, which element 1, 2, or 3 is a liquid at room temperature? And room temperature, it tells you, is 20 degrees. So which element, 1, 2, or 3, is a liquid? All right, so look right down here, a liquid. Pause the video, write down the answer.
Can I just remind all students that with the easing of restrictions, plans don't finish until...
Sorry about that. There was an announcement at my school here, so I just had to turn it off for a second. Yeah, so which one is a liquid? Pause the video and write down your answer. All right, so the one that's a liquid at room temperature here, you should have said element 2. Okay, now if you didn't say element 2, you're wrong, so you need to think about why you're wrong. Don't forget the rest of the question. It says justify your answer. So again, we're going to justify. Give a reason for your answer. That's what justify means. Why is it number 2 and not number 1 and number 3? So pause the video and write down a reason. Justify what the reason is. Okay, so here you should be looking at the temperatures. Okay, so room temperature is 20 degrees. Okay, now if it's going to be a liquid at room temperature, then it needs to be 20 degrees needs to be between its melting point and its boiling point. Let's look at this one for a second. Element 1. Element 1 does not melt until you heat it all the way up to 1538, which is a very high temperature. So that means it's a solid until you heat it to 1538. So at 20 degrees, it's definitely a solid. So it can't be that one. Let's look at element 3. Element 3 is a solid below minus 101. When you heat it up to 101, to minus 101, it turns to a liquid. If you keep heating it at minus 34, it turns into a gas, which means it's already a gas by the time it gets to room temperature. So 20 degrees is much higher than minus 34. So it's already a gas here at room temperature. So justify the reason why at 20 degrees, the room temperature makes element 2 a liquid. All right, so we'll probably say something like this. Room temperature, oh no, maybe not start like that actually. We'll say element 2 turns to liquid at minus 7 degrees C. It stays liquid until, and again, if you didn't have something like this, pause the video and say, when does it stay liquid till? Do that now. Okay, it stays to liquid until 59 degrees C. This is when it boils. So that's fine because 20 degrees is lower than 59. Therefore, it is a liquid when at 20 degrees C. All right, something like that. All right, so that there is that full question. Probably like one of the harder questions that we've done so far, but again, nothing that's not too manageable. It's just that it's got lots of little bits to it. And I suppose these types of questions are quite difficult where they put 2 parts together in one question and they don't show you that there's a different part. So you could easily just say which element is liquid. You could just say number 2 and not write your justify. If you miss this, then you're probably missing a lot of the marks. If there's 9 marks going for this question, it's probably only 3 marks going for saying 2, and the 6 marks is going for the justify. So if you forget to do justify because you're not reading the full question, that means you're only getting 3 out of 9, even if you get it right. So just being extra careful with the reading of those questions. All right, guys, so that's that. We'll see you in the next one where we'll have a look at question 16.